estimation. It's kind of pretty simple-minded stuff, but those are the notes. And now somebody wanted to have notes early. I don't know who it was now. You did, yeah. So usually I will hand out notes before covering the material. Not always, but usually I will do that. So if you want to read ahead, you can do that. I will also put up a website, and the notes will be available on the website, and then you'll be able to access them that way also. When I was in elementary school, we had a teacher, a horrible old woman, who used to take a ruler like this and hit the desk really hard and make a really loud noise. And one day she miscalculated and she hit the desk and broke her arm. Never did it after that. But it's interesting that is a sound when you do that. And where does it come from?
From the air. Vibration of the air.
Well, yeah.
And the desk.
More specific than that. It's a kind of a very sharp sound. When you clap, there's a kind of a sharpness there too. If you have a whip, big bull whip, there's a sharp sound on the end of that.
Breaking the sound barrier, isn't it? The tip of the whip.
The whip, that's right. The tip of the whip goes so fast that it goes faster than the speed of sound in air. And then it creates
Sonic boom.
a shock wave, right? And it's that shock wave that is the sharp sound. And same thing happens here. Interesting to speculate on exactly how it comes about. The whips were actually used not to hit the animals, but just to make a noise so that we go away from the noise. So when they had teams of oxen and this big line, boom, ox hears the noise. Okay, so the first thing that I want to ask is the following. So okay, we said that we can express everything in the world in terms of the 5 basic dimensional quantities. So let's do an example. Express magnetic permeability mu naught in terms of these. In terms of basic dimensional quantities. Okay? If you can do it for everything, you must be able to do it for this. So what is mu naught, first of all? So we'll be talking about liquid crystals and electric fields, magnetic fields, temperature. So we've got to get used to working with electric and magnetic quantities right from the beginning. What is mu naught? Epsilon naught. What's epsilon naught? Nobody knows
It's
that.
a constant describing the force between two charges.
Well, epsilon naught appears in Coulomb's law. That's certainly true. What about mu naught?
Maybe something related to the magnetic. Is
It's a constant ferroservers.
Well, okay, so first of all, there are some fundamental units in physics. Okay? Speed of light is one of them, gravitational constant. Mu naught and epsilon naught are also such quantities. Really important.
Free space.
Really important, yeah, they tell you about the electrical and magnetic properties of vacuum, of nothing, free space. Okay? And mu naught is, does anybody know?
How this object is responsive to the magnetic field?
Hmm?
It is described how from subject teacher
Right.
responded to the magnetic field.
Exactly. It tells you how free space, how nothing, responds to a magnetic field. So does anybody know the magnitude and the units? Epsilon naught?
It's 4 pi, mu naught 4 pi 10 to the minus 7.
Mu naught?
Yeah.
Okay, it's good. 4 pi.
10 to the power minus 7.
Good. Good, very good. So, but you've been with us for almost a year. And the units are?
That's good.
The units are Henrys per meter. Henrys. What the hell are Henrys? But that's what it is, Henrys. SI units, Henrys per meter. Okay, what about epsilon now?
It's probably something similar, but coulombs per meter. Or, no, wait,
1 point
Farad,
3 10 to the minus 12.
probably has something to do with
Farads,
capacitance,
right?
right?
Yeah,
Okay.
something.
Capacitor has
Farad.
farad, so it's probably farad per meter.
Yeah, good. Yeah, very good. Farads per meter, yeah. And the number?
1.38 10 to the minus
We're mixing here.
I think it's 0.85 or 885 and 10 power, I don't remember. So there should be 8.
8.85 10 to the minus
8.85 times 10 to the minus 12. Right. Farads per meter. Okay, so that's also an SI unit, and it's also kind of useless. We don't know what that means. But we use sort of farads. I mean, we understand a little bit about capacitors. So, what are Henrys a unit now?
Inductance.
Inductance, yeah. So, yeah, the world is kind of symmetric. There's electrical things and magnetic things, capacitors, farads, inductors, coils, and Henrys. They're kind of equivalent. But people, for some reason, love capacitors more than they love inductors. I don't know why. But everybody knows about capacitors, and hardly anyone knows about inductors. And it doesn't seem fair to me.
Inductors are a pain to work with.
Not at all.
You gotta worry about this field around them that can affect other pieces of
And
equipment.
capacitors, no.
Well, the charge is held within the capacitor. I mean, there's some that gets
The
out the
fields
edges.
leak out just the same. One way, so maybe not just the same, but pretty close. Anyway, okay. It's true that you have to be careful with inductors, but capacitors also. Yeah, in fact, when you make circuit, there's always a problem. In 2 wires, there's capacitance between them, and in some cases, that's really vital. Also inductance. Okay, so that's it. Now, we want to be able to express this guy in terms of the 5 things. So the 5 things are kilogram,
Second.
meters, seconds, amperes, Kelvin. So how do we do it? There you are. Candidates, the exams in front of you. What do you do?
You have meters on the bottom, and that's good, because that's all we got. So we'll call it a
It's
day.
good. You rejoice at the little nugget of value that you have. Okay, so now, okay, so how do we go about finding out what Henrys are?
From the definition.
Yes.
You can think from the basic point about the current. The current will reduce the magnetic field. A simple model which can be using is to remember what it means.
Right. Right.
The most
So-
simple. For example, current pass through the space, and I remember that there will be some kind of magnetic field around, and then you can start from such a simple.
Right, that's right. That's really good. And that's exactly what you need to do, is you need to think of some equation where mu naught appears, right? Then you have some idea of writing mu naught in terms of other things which you know better. So, for example, in the case of a capacitor, what is the capacitance of a parallel plate capacitor?
A epsilon by d.
Hmm?
A epsilon naught by d.
Right, so it's epsilon naught times the area divided by the spacing, right? Everybody knows that. So as soon as you have this, then you can already relate farads to other things, right? So this is good. Now, we need to think about an equation that has mu naught in it. And I don't think anyone remembers the equation for the inductance. So I won't propose that. But there are simple equations which we know, and one of them is just the B field inside of a coil. So just take a paper tube and you wrap copper wire around it, and you pass some current I in here, and you want to know how big the B field is inside. So how big is it? B equals, does anyone remember this?
Well, it has number of turns in the top. It has diameter in the bottom, right?
Maybe we can
It
remember.
has.
You're improvising a little, but
I'm
it's
absolutely,
not bad.
I'm absolutely improvising.
But first of all, what about the current? The current
Well,
makes the magnetic field. right?
current is in the top.
So there has to be an I here somewhere.
This isn't the simplest way, I think.
Hmm?
I think it would be easy if we recall the force of interaction between two straight
Wires.
wires. Yes.
Force? Well, how long are the wires?
Force per 1 meter. Let's
Force per length, yeah.
say. Yeah.
But I think this is something which is
Well,
pretty
at least
familiar with
there
most
won't
people.
be this B.
Huh?
We won't have one more variable B. There
I
will be
know.
only currents and distance and so on.
And force.
And the force. But unfortunately, I don't remember that.
Let's pursue this, so maybe we'll go back to that. So what goes in here then? It has to do with the number of turns.
The number of turns is in the top. The more turns, you get a stronger B field.
So this is just mu and I. Okay, that's a really simple expression that I thought most people knew, you should know. That's really a very common expression. So it's true that it involves B, which is another kind of an unknown. But nonetheless, it involves mu, which is good, current, which we know, and N. What is N?
Number of turns.
Number of turns.
Number of loops.
Per
Number of loops.
turns per length.
It's a number of turns per length.
Right.
So N is number of turns per length. And it's a pretty interesting equation actually, because it doesn't depend on the area. So it only depends on how much current is flowing really, right? That's really all it is. The number of turns per length tells you how much current is flowing per length along the top. Okay. All right, so if we knew what B was, we'd be in business. And as you say, we don't know what B is. So we need another something. How do we figure out what B is? Well, we need some other equation that tells us what B is.
Lorentz force, for example.
Lorentz force, very good. So what is that?
F equal Q V B. Q times V times V.
F equals QVB. QVB. Is everybody happy with this? What is a Coulomb force?
Equals QE.
QE, right. The force on a charge usually has these two pieces, QE plus QVB. And it's a vector, and it should really be V cross B.
But that's only for magnetic field, and
Hmm?
that's only in magnetic field, right?
That's right, there's no electric field, it's just this.
Plus,
Okay.
we need only dimensions, so we don't need that.
That's right, so we're ignoring the vector part of it too. Okay, so now we're in business, because we can write B in this way, and we can write mu naught. So we can write mu naught has units of B over Ni, and B we can write in this way, it's F over QB. So we have F over QB, that's B, and then we have Ni at the bottom. Okay, so, well, that's pretty good. We don't quite have things right, but we can make everything okay now. We can write all of these things in terms of the basic dimensional quantities, right? So what is force, for example, in terms of these guys?
kilogram, meter, second.
Force is mass times acceleration, right?
Yeah.
So it's kilogram, acceleration is mass divided by time squared. When you're going to decide whether we're going to work in units, fundamental dimensional quantities or not. So let's do that. So let's work in, this is mass times acceleration, which is length divided by time squared. That's force. And here we have charge. Now what is charge?
Current plus time.
Current
That's by time.
times time. Right. So this is IT. Everybody happy with this? And then velocity is
That's all time.
Meter,
length divided by time.
Time.
And then number of turns per length is
No.
1 over length.
Uh-huh.
And then this is just curve. Right? So let's simplify this a little then. So we have mass, and then we have these lengths cancel here. So we have a length on top, and then we have a t squared here, but these guys cancel. So we have I squared t squared. So the fundamental units then are going to be kilogram meters divided by ampere squared seconds. So Henry per meter is the same as kilogram meter divided by ampere squared second squared. Okay. And we have to be able to do this for every quantity that we encounter. We have to be able to reduce it so that we can write it in terms of these 5 guys here. Okay, and that's a really important thing to be able to do. And again, the rule, I think, is to find some equation that contains the quantity that you're interested in terms of things which you either know or things that you can write in terms of other equations in terms of things that you know. Okay? So this then is the next kind of step. We have these 5-dimensional quantities, and we need to be able to express everything in terms of these. And this is something, too, that you should practice, because you need to be able to do this pretty much routinely. Now, I don't want to do more examples, but all of you should look at various things, epsilon naught. Go through this kind of argument, express it in terms of the 5 basic dimensional quantities. Okay? Everybody happy with this? So the thing is to find some equation that involves the thing you're looking for, and then you can always reduce it to these 5. Okay. Let's move on. So I want to, we only have 12 minutes left. So I want to do quickly one example putting dimensional analysis to work now. So now we look at a real problem and we use dimensional analysis to get a solution. So the problem is this. Okay? If you look at the ocean, you see that there are waves moving on the ocean. And the question is, what is the speed of the waves? How fast do they go? So, what is the speed of water waves in the deep ocean? So certainly the waves are there, and they certainly have a speed, and they move at a constant speed. So now, the equation that describes the motion of liquids is Navier-Stokes equation, which is really pretty challenging differential equation to solve. And one way to solve this problem would be just that, would be to try to solve this differential equation and come up with some answer. But when you did that, you would write that the velocity of these waves, so what you're looking at is here's the ocean, water here, air here, and there are waves. And these waves are moving at some speed. The question is, what is this velocity? So if you solve this differential equation, put in whatever you have to put in, you have the answer, you can write it down. The velocity is equal to something. And our business is to figure out, essentially try to guess what the something is on the right-hand side. And so, the first thing you want to ask is, what could be here? What are the relevant quantities here? So what are the relevant physical quantities that somehow come into determining how fast these waves go? And this is really the challenging part. This is where you need physics, this is where you need intuition to be able to determine what the relevant physical quantities are. So let's talk about this. Let's try to figure out what these are. Why do waves move at all?
Throwing medium of restoring force.
Yeah, I mean, if I just took a fish tank half full of water, and somehow I managed to make the surface look like this, and then I let it go.
It wants to go into a lower energy state, so.
Right, it's not happy where it is. It wants to do something, and so the water will go down, and the waves will move away from that. And so, what is the driving force for this?
Gravity.
Gravity. Right. So, gravity must come into this picture. If there was no gravity, then it could be that the water would just stay like that. So, acceleration of gravity, we expect that to play a role. What are the units of that?
Acceleration.
Yeah, just acceleration, just meters per second. Okay, what else?
Probably wavelength.
Wavelength? Good. Yeah, that's a good point. If you look at the waves, you see that the little short waves go at a different speed than the big ones. So wavelength is some kind of length. That's good. What else?
Density of air and water.
Density, well, certainly the density of water will play a role. Because the wave moves because gravity is pulling the water down. The bits that are high get pulled down. So the density of water comes into it. And we could go on. We could think about other things. The density of air, but probably that's not so important. Right? I mean, the density of air, what is the density of air? You brought it up.
A lot less than the density of water.
It's
For what?
28 gram per kilometer.
How much?
28 or 29 gram per kilometer.
Per cubic meter. At what temperature and pressure?
A normal temperature, 110.
Is that right? You want to know?
29.
The turns out to be almost exactly 1 kilogram per cubic meter. It's quite a lot. It's surprisingly high. So,
1 kilogram?
yeah. Yeah, 1 kilogram.
So does the pressure from the atmosphere make a difference in this?
Well, that's a good question. But my guess is no, because, well, I don't know. My guess is the lowest order, not much. Now, there's other effects, obviously, that come in. Some people bring up viscosity, and viscosity could contribute. Surface tension is something else. If you take a flat interface and you make it much longer by putting a wave on it, right now it's longer than when it's flat, then you have more surface tension plays a role. And sometimes surface tension is important. So things like surface tension, density of air, pressure, all coming through. But let's try to see if we can make things work with these quantities. Okay? And one way to do this is just to try to put them together somehow and see if it works. The other is a little more systematic, and let's try to do it that way. So first of all, let's write these guys in terms of the basic dimensional quantities. So this is just acceleration, length over time squared. This is just length, and this is mass over length cubed. And so suppose that we agree that these are the relevant quantities. We'll guess at these, and now we want to figure out how to combine these to end up with something that has the units of velocity. And those guys have different units, so we can't add them together, right? You can't add an acceleration and a length. It just doesn't make sense to add things together or to subtract them. They must be the same kind of thing. So all we can do is either multiply them together or divide one by the other. So what we can do then is just to say, okay, let's suppose that the velocity is the acceleration of gravity raised to some power. It could be g squared or q, or it could be raised to the power of -1, in which case it would be 1 over g. Or 1/2, absolutely. So something. So we can just put in some unknown exponent and then see, so lambda to some other exponent and rho to some other exponent here. And then we can just try to figure out what these exponents have to be to end up with something having the right terms. So now if we put in the actual basic dimensional quantities, we'll have L over T on the left-hand side for velocity. G is L over T squared, so we'll have L over T squared to the power alpha. Lambda is just L to the power beta, and rho is mass over L cubed to the power gamma. And so for this equation to work, we have to have the same power of L on both sides, same power of M, same power of T. Right? That's the only way it can work. Everybody happy so far? We're almost done. So, well, let's start with L. If we look at L, on this side we have an exponent of 1.
I think we can start with m,
You want to start with M?
because gamma is 0, obviously.
Right. Right. So if you start with M, you can see right away that there's an M here, but there's no M here. So the only way that can be is if gamma is 0. So right away we look at M, and that tells us that gamma must be 0. Good. Next we look at L. Can I look at L next?
T or
Huh? T?
T.
Okay, T. Let's look at T. What do we have? On this side, the exponent of T is
minus 1.
-1. And that has to equal
Minus 2 alpha.
-2 alpha. And that's it, no other T anywhere. So this tells us that alpha is a half. And then finally, we look at, what, nothing, we're done.
Better.
Beta. Right, you have to look at that. So we have 1 on the left-hand side, the exponent of L is 1. And here we have alpha plus beta. We already know what alpha is, so we got that beta is also half. And we're done. So now we have found, we've solved those little equations, and we found that gamma is 0, and alpha and beta are both a half. So we find that the velocity is the square root of g lambda. So that's a really interesting and kind of a beautiful result. And we haven't done any serious physics other than identifying the relevant physical quantities. And it turns out that this is true except for a factor of 2 pi, which is pretty remarkable. And one amazing thing is that it doesn't depend on the density of the material. That's really surprising. If you have a sea of mercury, a sea of water, waves will propagate in the same way.
Is there any possible constant in front of the...
Hmm?
Is there any possible constant in front of the...
There is, yeah. And that's what I was saying, that we're off by something like 1 over 2 pi, I can't remember now. So we're off by a dimensionless number here, okay, which is typically the order of unity, right? And so there's no way to get that from dimensional argument. Okay? But so it's a really interesting result. It means that waves on the moon would travel a lot slower than on Earth, and long wavelength waves go faster than short wavelength waves. And the speed doesn't depend on the amplitude. Small waves with a given wavelength and big ones go at the same speed. And these are all things that you can check in the lab. So you can get a lot of physical content just by making these dimensional arguments.